Thank you all for coming. Thanks for the organizers for inviting me. And my name is Shaked Shama, and I will present resource-efficient driving policy. And this is joint work with Shai Shalev Schwartz and Amnon Shashua. Both are also from Mobileye and the Hebrew University. And I will start with a brief consideration of the motivation behind developing autonomous driving, and those things will come back later at the talk, and they will define different components of the solution. So the first thing we want is to achieve comfort for our day-by-day use. We spend too much time on the road, of course, and it will be much better if we could all do some productive stuff or enjoyable stuff instead of just sitting in traffic and being, angry and all that. The second thing which we will want from an autonomous driving system is to be safe. And as we all know, human error is a huge factor in car accidents, and we would love to eliminate that and to save lives and decrease fatalities on the roads. And autonomous systems are doing lots of things much better than human beings, and we would like them to do that better than us too. So how would you decompose a solution for autonomous driving? So the first part you'll need is the part of sensing. You'll need to understand the present around you. You'll need to detect different road users. You'll need to have a map. You'll need to have all of that in order to have your sensing state, and then decide what you're going to do in it. The second part is the driving policy, which is about planning for the future. It's about taking this state, this present, and trying to do something useful about it, and output some desired trajectory in the world where the vehicle will want to travel. And the last part is the part of control, which takes this trajectory and tries to fulfill it as comfortably as possible. So why is this a resource-constrained setting? So I think that most of you will agree that the components of the system must run very, very fast, because we can't, send something to 50 GPUs, wait for 2 seconds, and then get an answer of what we should do. Things should run very, very fast. We need to control the vehicle in real time, just as we humans do. The second thing is that it is best to do it on a cheaper hardware, because we would like to have the solution be scalable as much as possible and cheaper as much as possible in order to deploy it in millions of vehicles. So in order to get that, we will need efficient sensing technology. So that includes mapping for static sensing, and dynamic sensing for dynamic objects. And here we will focus on the implications of the resource constraints over the planning and the policy component of the system. So the first thing to ask is, what's the problem? Driving is a simple thing that every person can do, or almost every person can do. It's not like playing chess. It's not anything complex. Is it any hard at all? So this is a video taken from a drone in a junction in Jerusalem, and these are human drivers. And maybe you've missed what happened there, but you will see that in a second too when we'll zoom in. And you'll find out that even human beings are not very, very good with their driving policy. And they are probably now shouting at each other, and suddenly things are solved. Sorry. On the other hand, human beings do some amazing stuff, and here they somehow manage to, push their way. There is no structure. There are tens of agents, and here this is even crazier. Somehow everybody communicates perfectly, and even the cow over there can pass the junction safely. So we would like to get to this, and I don't want to even think of hard coding such behavior. So a few points to sorry? So we can look at the challenges in a few points. I think the first one will be the balancing the trade-off between being defensive and aggressive. So on one hand, you need to be very cautious, and you need to be prepared for some unexpected and possibly dangerous situations. On the other hand, being too defensive will mean you'll have to stay in your garage, because some dangerous stuff could happen, and yet we all go on the roads. We also need to understand how to negotiate and communicate with other drivers and other pedestrians, and perhaps, I mean, that could be maybe easy because we can use the blinking lights and so on, but the harder part of communication is to understand what they are trying to communicate to us, and sometimes they won't blink, they will be unexpected, they won't drive smoothly, and we should understand what they are going to do. Another thing is somehow understanding the rules of breaking the rules. So, for example, in a roundabout, you should not push your way into the roundabout. People which are already in the roundabout have the right of way. However, if you'll do that in traffic jam in the morning, you'll have to stand for half an hour and not move. So somehow it's okay to push your way into a very, very packed roundabout, and we should understand what are those rules which allow you to break the rules. The last thing is understanding how to deal with uncertainties, which we cannot already sense at the present time, and we should be prepared for so many different dangerous scenarios, and this is a very big challenge. So, of course, let's use learning. That is, of course, the best thing to do. So I'll go very briefly over basic definitions and reinforcement learning, which I'm sure all of you know. So our goal in reinforcement learning will be to learn a policy, which is a mapping from states to actions. And the framework of the game is that at each time step, the agent observes a state, ST. It chooses an action, AT, based on some policy, which is this mapping from the states to the space of actions. And the environment will move the agent to the next state, ST plus 1. And the agent will receive a feedback for learning, which is a reward signal at each time step. And the goal will be usually to maximize some discounted reward or cumulative reward, and so on. And I want to define the queue function maybe in a more abstract way than what you are used to from regular MDPs. And we can think of it as simply qualitating, taking some action A when we are at a state S. So Q of SA will be the expected future rewards, and let's not dive into details whether they are discounted or not or all that. And it is very intuitive that if we want to maximize the future rewards, it is best to take the argmax of the Q function. And of course, autonomous driving is not an MDP because it's a multi-agent game, but we can think of it in an agnostic way, and our goal is simply to find some qualitative function which will help us to somehow choose a good action. So there is no guarantee that it's optimal or anything like that. So our problem will be how to obtain this Q estimation. And the challenge is that this future effects of a certain action which we are taking at time t depends on a long time horizon. So it's very hard to estimate what will happen in the future. There are so many outcomes which we can't see based on the local state we are at at time t. And perhaps some explicit examination of the future, which we can call planning, can help us here. Okay, so we should somehow explicitly look into the future outcomes, and this could help us understand what will happen. Yes, please.
Actually, maybe you could correct my intuition, because I felt that the time horizon is actually quite short. It's just the uncertainty of what might happen after.
No, of course that you repeat your planning on a very short frequency, but very high frequency. But the future effects can only come into the picture in a few seconds' time.
Yeah.
So I can do something now, but I don't know if it will help me to push my way into the roundabout, which will happen only in 5 seconds. Or, yeah.
So, just a follow-on question. I didn't entirely understand. So, is it that you're basically aiming for an end destination, maybe tens of kilometers or away, and also thinking about the roundabout? Is that two separate?
So you could think of a very global reward which you get when you get safely back home. That could be one way of one feedback which you could get. But you could also separate the problems into sub-problems, and your goal now is just to cross this roundabout and get out in the second exit.
And
Okay,
can you have a
for example.
reinforcement learning function call a reinforcement learning function like that?
You could do that, yeah. Of course, like in hierarchical model or something like that. So, getting back to planning, the main question is to what extent do we plan? So let's assume that if we take an action AT, we will surely be brought by the environment to state ST+1, some state. So it is very hard to qualitate the whole future only based on this. But if we plan further and we start considering what will happen when we will be at ST+1 and take some different actions as AT+1, we will get to different states, ST+2, and we start gaining more intuition and more understanding of what will happen in the future. And was AT good in the first place to bring us to ST+1? However, if we look further, we can much better tell how good was the local action, but suddenly we start considering more and more future trajectories to the extent that it will take forever. And we can't do that because we don't have time. We need to decide very, very quickly what we are going to do at each time step. So to put that in an organized manner, so the first attempt will be just to plan as much as possible, and to roll out the possible future trajectories, and therefore get a very good estimation to the quality of a certain action. And this is very successful in state-of-the-art RL applications, such as AlphaGo, which made a lot of buzz and was very successful. And it allows you to have some sort of complete view of what will happen in the future, and it's a very thorough approach to planning. The problem is that this is very, very computationally expensive, and even with smart rollouts, such as done in AlphaGo, so lots of supervised learning, lots of reinforcement learning involved there, lots of computational power, and it is very, very computationally expensive, even in a very smart rollout strategy. The second attempt could be just to use function approximation in an end-to-end manner to approximate Q. So just give me a state and tell me the quality of a certain action, and this could be, for example, a deep neural network. This is very computationally efficient, so in runtime you just run your network. And this is also very successful in numerous applications, such as playing Atari games, in deep Q networks. And this could also be a good solution, but as we said earlier, this implicit folding of the whole future outcomes into one queue is difficult without explicit consideration of the future. And also, we lack guarantees over the future outcomes, and something really bad could happen if our network does not perform as we want it to. So we need to somehow balance between those two approaches, and we will address 2 points here. The first one is how to provide guarantees for future outcomes without completely traversing over the whole future outcomes which could happen. And the second one is how to plan smartly for our efficiency. So let's think about the safety problem in autonomous driving. So driving is a dangerous task, and some things just can never happen. We don't want to allow them to ever happen. So let's define a state S to be unsafe if there is no way to escape a future accident when we are at this state. And of course, if we roll out all future trajectories, we can be sure whether a state is safe or not. If we look into infinite amount of time, we will be able to tell that. But we cannot provide this guarantee when we use a function approximation approach, for example, and even if we use like some sort of a smart rollout technique, still something really bad could happen in the future. So this is a video which actually tries to learn. It was our first attempt to try to learn to change lanes, and we did not define anything special for safety, and it was very, very close. And we don't want to allow such behavior because it was too close to being fatal. We want to have guarantees that some things will never happen. And why is it hard to learn it at all in the first place? We should think of large-scale learning algorithms, and those algorithms which we usually know are very good at minimizing some expected loss or maximizing some expected reward. However, assume that typical loss values are in plus minus 1, and they are bounded, and assume there is a very rare event, such as an accident, which has a probability p, which is very low. So in order for this event to have any effect on the expected loss, we need its order to be huge, of order 1 over p, And stochastic gradient methods, which are basically the methods for optimization, which we are using now, are suffering from this large variance of the gradient estimate, which controls their convergence rate. So our solution for this is to decompose the Q function and write it as a sum. The first part is Q safety, and the second is Q comfort. So,
Do you have to describe
sorry?
Do you have to describe what states are bad?
Sorry?
That is, would you have to hand code what states are bad?
No, you will not have to.
How do you know what state?
So that will come in a second. Okay. So the first part, Q comfort, represents just the average case quality of taking an action at some state. So this could be like, do we drive at a certain speed? Do we get to the required route? Is it smooth? And so on. And Q safety represents those rare case properties of a state, and which says, is this a very dangerous thing to do? And it has a completely different scale of reward, or a negative reward in this case. So in order to estimate Q comfort, it is possible to learn an approximation for it, because it should be good on average. And in order to do this, we use several different approaches in order to balance between longer and shorter term planning, and provide semantic meaning for future trajectories. So for example, there are many future trajectories, as we saw earlier, but many of them can be considered as take over this car and change lane later. So if I don't want to take over that car, I do not need to consider many trajectories. So the decisions this is a very good way to prune the tree which you are planning over. A second thing is planning in a semantic state space, which decreases the size significantly. So you could plan in a state space which, for example, is continuous and has the positions of the different agents. Or you could plan in a space which just says for each agent, for example, is it near me, very close in front, regularly close in front, or very far in front? And usually this will be enough for you in order to decide, I want to overtake it, or I want to change lane. And then you will be able to decrease the size of your planning space very rapidly. And also, there is no variance problem due to uncommon values of the loss, because everything is of roughly the same scale. So what about the safety part, which we were asked before? So recall the definition. So S was safe if there was a way to escape a future accident when starting from it. And of course, it may be suboptimal, but if there is a specific maneuver which allows escaping an accident, then it is safe. So this is sufficient. And intuitively, what do humans do when they try to avoid accident? They don't do very complex policies. They usually push the brakes as strong as possible. So that leads to intuition that we can define a very small set of emergency maneuver, and it will be very expressive. So, so what we are doing is we are checking whether a small set of predefined such maneuvers contains one that ensures safety. And based on this, we estimate Q safety. And this check is rule-based. and nothing is learned there. So there is no learning, and it is kinematics and solutions to optimization, convex optimization problems. And actually, we are just working on, I will promote a paper we are finalizing these days, and I think will be published in about the following few weeks, which we are, in it we do formalize all of those checks and prove indeed that they provide safety, and that this local verification of safety is sufficient. And as we said, it is very intuitive that a very small set of emergency maneuvers could be very expressive enough, because we humans use very small sets of emergency maneuvers. So to sum up, autonomous driving, and specifically the driving policy part, is very resource constrained. It is a difficult task, and we want to use learning for this difficult task. The distinction between comfort and safety allows this, because now we can use learning for comfort. We can do anything we want for comfort. For the comfort part, we need to balance between the ease of quality estimation, which we obtain from very thorough planning, and on the other hand, the efficiency of quality estimation, which we must have. And we should develop efficient mechanisms to provide guarantees over the outcomes of the actions. And as I said earlier, this will be in our soon-to-be published paper. So thank you. And just meanwhile, you can see this is, for example, a scenario where the red cars are trying to merge to the left, the blue ones are trying to merge to the right. They don't know what is the color of the different cars. They only view how they are moving in the world. They actually only know if they are, I think in this version I have 7 semantic meanings of distances. So you can be near me, and close in front of me, and very far, and also behind. And as you can see, I'm running it on my very non-dedicated machine, and I'm running all of them, and it is very, very, very efficient. So you are all welcome to ask any questions. Thank you.
Questions? So in general, like at least so far, like the planning system that you told about has not really addressed any questions about, say, adversariality, right? So let's say I am a competitor company and I just want to, make life very difficult for you by just causing 1 or 2 accidents, where I pick up that if you see certain signal, then you do something crazy. Right? And so you ensure that. And
yeah, our safety definitions do involve some assumptions over some, you can call it non-adversarial behavior of different agents. And you can think of that also even in the road. I mean, there are any of us does not ensure safety. Okay, so we are driving in a traffic jam, and someone behind us can crash into us if he is an adversarial, but it won't be our fault, right?
No, but here the thing is that because some of the triggers that you have are dependent on what you sense in the world, right? So let's say if your competitor figures out that if the next car is driving, say, let's say more than 20 miles per hour, or say somewhere between 20 to 20.5 miles per hour, then some of your triggers work. So if it finds that out, then it can try to exploit that.
Mm-hmm.
Whereas for humans, it probably won't happen, and even if it
But
happens,
will
it
you
will
buy
happen
their
very
car?
quickly.
Will you buy their car? I mean, in order to, we need our mechanisms to be reasonable, and if they are reasonable, then probably in order to fool them, you will need to be very aggressive or something like that, and you will not want to buy a car which is being very aggressive in order to fool a different car.
No, they're not maybe soundness claim, right? You will need a claim that the set of rules you are coming or set of assumptions that you are coming are really safe, they're sound. And like, so is that the case currently?
Yeah, they are sound. They are reasonable.
Once you make the assumption, then you're saying that your system is sound in the sense that the system will definitely follow those assumptions or follow the rules.
Mm-hmm.
But why is that set of rules complete? Why is that rule sound?
That is something that is about common sense. Okay, so and what do I mean by that? I mean that of course I could define many rules. I could define that if anyone is on the road, then it's not safe. This will not be common sense, and no regulator will, customer will not take this. On the other hand, many rules which we could devise would not be accepted by any regulator. Okay, so you need to balance it somehow, and to obtain some set of rules which will be accepted by society probably, and will define the required behavior or the standard from an autonomous vehicle.
Yes, go ahead.
The standard is very different. Even in the US, for example, driving in Boston is very different from driving like Los Angeles. You know, I don't know, probably in Jerusalem.
Mm-hmm.
The standards are different.
I agree. I see, and maybe a follow-up. So I'll just answer the first question. Yes, they are different, and maybe regulators in different countries will adopt some of the rules and not all of them. However, I think that we are less dealing with what is customary in different countries. That is more like comfort. Okay, this safety thing is like the last resort. Okay, so you will need to be very dangerous in order to be non-safe. Okay, and that will be non-dangerousness, which is worldwide and global. Okay, and of course the comfort part could be different for different countries. So in some countries you will want to be a little more far away from somewhere else, and in different countries you will not be afraid to push yourself a little further, as long as you are safe. And to be safe is like the last resort. It's pushing the brakes as hard as possible with a response time which is very fast, and you will not want to drive in a car which is only safe and not comfort.
But I guess, I think the intention of the question, if he can correct me, is that when you're a human being, every human being has a different standard for what is safe. Whereas as a
although
self-driving
there
car,
are laws.
But as a self-driving car, you have the lowest common denominator. You have to be safest than the safest human, right? In a sense. So,
however,
so
you are
there
not.
isn't no such universal standard, because human beings themselves are different.
I agree,
So
but
what is
and
safe
usually when you will have a car accident, you will have some I don't know, court of law which will decide who was to blame for the accident. And I agree that different judges could decide different outcomes, but I think that what we would like is to have some standard which will be acceptable and standardize this. And,
You had a question.
which algorithm for this? Oh, they sense the environment using cameras and radars and to some extent lidars, and mapping, which is by our RAM technology.
What's the representation? Is it objectless? Is it straight
So we are playing with that a lot. It's usually not like a top view image or something that is fed to convolutional neural network, but a list of features. And those features we are striving to have them as semantic as possible. So, because this makes sensing much more accurate. It is much easier to say this car is very far than saying this is 83 meters away, or something like that. And it decreases the state space significantly.